Welcome back. In our last video, we fell in love with paging. It was simple. It chopped memory into neat, fixed size 4 kilobytes blocks. But there is a problem. Imagine you baked a beautiful 3-layer cake with a buttercream icing flour on it, and paging takes a butcher knife and just chops your cake into squares. It doesn't care if it cuts right through the middle of a decoration. It ignores the structure of the cake. But programs do have structure. They have code, data, and stack. So, is there a way to manage memory that respects the logic of the program? Yes, it's called segmentation. Unlike paging, which is physical and rigid, segmentation is logical and flexible. The core idea is that instead of fixed-size blocks, we cut memory into variable-sized chunks called segments that actually match what the program is doing. Segment 0 for the code. Maybe this is 50 kilobytes. Segment 1 for the global variables. Maybe this is 20 kilobytes. Segment 2 for the stack. Maybe this is 10 kilobytes. The OS allocates exactly what you need. No more, no less. The page table is now a segment table. We'll talk more about it just a few seconds later. So, now look at the address translation process with segmentation. When the CPU generates a virtual address, now it is logically composed of two parts, segment number and segment offset. The segment number identifies the logical unit of the program, like code or stack. And the segment offset is the distance in bytes from the beginning of that segment. Now, the MMU uses the segment number to index the segment table. Here, the segment table holds the crucial mapping information for each segment. Base address, the physical starting address, or the real location in RAM where the segment is loaded. And length, the size of the segment. Now, before translation can occur, the MMU performs a critical check using the segment's length retrieved from the segment table. The hardware checks if segment offset is greater than or equal to the length. Now, if the check in step 3 fails, which means the requested segment offset is greater than or equal to the segment's length, the program is trying to access memory outside the boundaries of its assigned segment size. Now, the MMU immediately triggers a segmentation fault, often abbreviated as Segfault in programming. Imagine segment 1 is 500 bytes long, but your buggy code tries to read offset 600. In paging, you might accidentally read the next page. In segmentation, the hardware checks, is 600 greater than 500? Yes. It kills the program instantly to stop you from reading memory that doesn't belong to you. This segmentation fault is the ultimate powerful protection feature because it instantly halts the program, preventing a bug in one part of the code from reading or corrupting the data or code of another segment or another program. This is the ultimate safety net. Now, at last, if the validation check passes, the final physical address is calculated combining base address and the segment offset, and then it's sent to RAM. So now, talking of advantage, as I've just said, excellent protection. Segmentation prevents a program from ever accessing data outside its logical bounds. Also, no internal fragmentation. A 50 kilobyte segment takes up exactly 50 kilobytes, unlike the paging. Now, you might be thinking, this sounds perfect. Why don't we just use this? Because of the fatal flaw, external fragmentation. The problem is imagine your RAM is a parking lot. You park a bus, a bike, and a truck. Then the bike leaves. You have a tiny empty spot. Then a massive semi-truck tries to park. It doesn't fit in the bike spot. Though all over, you have that enough space to fit that. Like this, over time, your RAM looks like a checkerboard. Because segments are of different variable sizes, when a segment is unloaded, the free space it leaves behind is also of a variable size. You have plenty of total free space, but it's scattered in tiny, useless holes. You can't use it. This wastes memory. For example, you might have 50 kilobytes of total free RAM, but it could be split into 10 5 kilobytes holes. If a new segment arrives that requires 20 kilobytes of contiguous memory, it cannot be loaded, even with 50 kilobytes available. So, we have a dilemma. Paging is great at managing space, but has no logical protection. Segmentation is great at logical protection, but is terrible at managing space. So, what do Windows, Linux, and macOS do? They use both. Modern operating systems running on dominant architectures, particularly Intel x86 or x64, employ a hybrid approach to virtual memory. This design uses the strengths of both paging and segmentation, though paging is the true workhorse for memory management. We use segmentation for the view. The OS sees the program as logical segments, code, to set permissions, like read only, execute only. Specific segments are still used to provide hardware-level protection to ensure that a program cannot accidentally or maliciously jump into the operating system's memory space. But we don't load those huge segments into RAM directly. Paging remains the primary mechanism underneath for translating virtual addresses to physical addresses, managing RAM, and preventing external fragmentation. We get the safety of segmentation with the efficiency of paging. That is modern engineering. So, let's wrap this up. We learned that paging is the master of efficiency and segmentation is the master of logic. Now, where do you see these in real life? You see it every time you swipe up on your phone. When you switch from a heavy game like FIFA Mobile to Instagram, the game doesn't close, it pauses. What actually happens? The OS takes the pages of that game and swaps them out to your storage, the backing store. When you switch back 10 minutes later and it reloads instantly, that is the OS frantically paging in those 4 kilobytes blocks back into RAM. You are watching virtual memory in action. Think about Google Chrome. You have 20 tabs open. Each tab is its own process with its own virtual address space. If tab 1 crashes, maybe a buggy website script, does your whole browser close? Only that one tab shows the snap error. This is protection of segmentation at work. Virtual memory isolated that tab so it couldn't touch the memory of tab 2 or your operating system. Finally, let's talk about the dreaded blue screen of death or a sudden app crash. We usually hate these, but actually, you should thank them. Deep inside your Intel or AMD processor, there are segmentation rules, often called protection rings. They separate the user mode, your apps, from the kernel mode, the core OS. If a buggy game tries to write data into the kernel's memory segment, the hardware screams segmentation fault and kills the game instantly. Why? Because if it didn't, that bug would have corrupted the kernel and your computer might never turn on again. The crash didn't break your computer, the crash saved your computer. So, virtual memory isn't just a memory trick. It is the bodyguard that keeps your digital life stable. So, that's the end of today's video. If you like it, hit that subscribe button for more. I'll see you in next video.